Okay. So this is the 4 simplex, in case you want inspiration for imagining it. Okay. So in this 4th hour, I love all your questions. So I will try to leave as much time for discussion. So the plan is that then this afternoon we will have our final hour together, in which I will tell you about spin-foam cosmology. So I will give you a concrete example in which we use these amplitudes to do computations. And what I wanted to do now is just to sketch some results and some ideas and try to use this time also for discuss more general aspects, to discuss together the doubts you can have and make comments and so on. So I think at this point you have an idea of what the theory is about, what comes to define it. You can read this very compact expression. I hope you can repeat what are the ingredients that comes into the definition of the amplitude. And let's say that there are plenty of beautiful results that have been obtained from the classical limit. Something I wanted to tell you about was the coupling. So how this theory stays together with the rest of the physics we know, in particular the Standard Model and particles like fermions and bosons and scalar fields and Yang-Mills fields. So let me just say, I'm not going into the details of this, but I want to say a word about this. I have already anticipated the fact that if you want to look at the bright side of what is happening here, is that this theory is providing a natural cutoff for the infinities of quantum field theory. So in a certain sense, quantum gravity together with the theory of quantum fields fits well together. Also, okay, if you want to couple fields to this theory of quantum gravity, of course, you cannot do this naively, in the sense that fields are defined on a continuous fixed space-time. And what you are doing here eventually is to see the interaction between quantum fields living on another quantum fields, like in relation to one another, interacting with one another. We don't have the full back reaction of the matter fields on the gravitational fields, but we can couple these fields in a kind of straightforward way to this theory, if you accept that you need to go through a procedure that is similar to what you would do if you had to put these fields on a lattice. So again, we have this graph structure that is a truncation of the theory. So you also need to have your matter fields that are sitting on this structure. And the way to do so is actually quite nice. For instance, you can put fermions on this theory. Remember the fact that, by the way, that the only way in which you can couple fermions to GR is to use the tetrads formulation. So we are already in that thing. Here, what you want to do is to have the fermions sitting on your graph. And what will happen is that basically you want them to sit on one of your volume elements. So on a node, you put your fermion, and this fermion will look like a small extra leg, okay, in your graph. So what about the scalar field, for instance, the bosons? So for if you think in terms of what are the symmetries of these particles, is basically like taking two fermions and putting them together. So then this is like a link that connects two nodes. So these objects will be sitting on the links and on the faces of your spin network. So you can put them like a contribution to your final amplitudes, and something that we will see in cosmology with, for instance, in a recent work by Dongshui Wu and Mushin and myself and many collaborators. So we have used this coupling with matter for cosmology to describe a bounce in spin 4. So, okay, so it's possible to couple matter. One of the first results that have been obtained was in this theory was to see the connection with the part of quantum gravity that is better established, I would say, that is perturbative quantum gravity. So you can define a propagator for the graviton. But here you have to be careful because, so this is something that you obtain here in the low energy limit of the theory. What does it mean, low energy here? It means that you fix your space-time, and for instance, you take a spin network that represents just Minkowski space, flat space, and then you look for excitations on this space, and for instance, you can take an excitation here and an excitation there, and you look at the correlations between these excitation. So this is what comes into the calculation of the two-point functions, the graviton propagator, and so on. So beautiful, some of the first results that were giving confidence in this theory. So we were mentioning also things like radiative corrections that have to do with the renormalization. And then something I will talk about briefly later is also extracting the black hole entropy directly from this theory and doing cosmology. So I will see, I wanted to, as I said, I wanted to leave a space for just a discussion and to whatever is more interesting for you. But these are things on which I will try to focus a bit more in this hour. I wanted to start with the most important part of the story, because unless the classical limit is well defined, well, that makes no sense to talk about this. So let me add a few comments regarding the classical limit. Okay. Yep. Yep. So, of course, the classical limit can mean many different things, and we have seen also the fact that, for instance, at the kinematical level, we have already a sense in which we can approximate classical space-time by taking coherent states. And we have different choices of coherent states. For instance, I was defining the intrinsic coherent states where just the tree geometry is equally spread, but you can make other choices so that both the 3D and the 4D geometries are equally spread. It's a matter of, so, or you can define whatever coherent states that suits better the problem that you are addressing. So coherent states have a, so now I remember why I wanted to start with this. So when we define the coherent states, what we were doing in this, to construct them, was to pick up the case of the highest possible spin. And we say that, for instance, when you study the theory of angular momentum, this is something well known. in this case, we have experiments, right? So you look at all the different orbitals that are associated with different spins, and the more the orbital goes up in the spin, the more the corresponding shape of the orbitals, if you want, the Gaussian that corresponds to this orbital is more and more peaked, okay? So that's why the classical limit is associated with the high spin. There is also a theorem, a mathematical theorem, that says that when you have Dirac brackets between some operators, so the Dirac bracket has a limit as the Poisson brackets when you take spin high. You take the spin, the j that goes to infinity for your operators, and the Dirac bracket reduces in this limit to the Poisson bracket, okay? So this is just to add to the fact that taking very high j corresponds to take the classical limit. In our case, what does it mean to take very high spin? Remember, the spin is associated with the area, with the geometrical quantities. So what we are doing when we take very high j means that we are considering a very large geometry. It makes sense that if the geometry is very large, and in particular the ratio between your total area and the fundamental Planck area is very high, then you are in a classical regime. So careful, because this is an important point. And there was a lot of confusion in the past regarding the relation between classicality or the quantum regime and the truncation. Because you can have a very simple graph, like you can consider just a single a graph that corresponds that is dual to a very simple triangulation of space-time, like a single tetrahedra. And this tetrahedra could be either an object that is very, very quantum, or could be an object still quantum, but is semi-classical. Just depends whether you are taking a small spin or a large spin, okay? As opposed to making up large space-time by adding a lot of quanta, but all in the fundamental representations, okay? This is something you can do as well. It depends on the kind of things. Again, it depends on the kind of problem you are addressing. You can do both things. Again, so large J means classical regime, and large J is a proxy for H bar that goes to 0. Okay. So let me say again. Let me say something regarding what does it mean for H bar to go to 0. So in general, of course, everything is quantum. So in the real world, H bar is always different than 0, okay? But this is just a limit that means that we are in a regime in which the ratio between our quantity and our fundamental quantity in natural units is very, very large. So we can disregard the effects of H bar. So H bar that goes to 0, if you have a generic theory like, I don't know, you have photons, you have whatever, it's your favorite quantum theory, in which you have discreteness, because so you see quanta, you have fuzziness, and you have probabilities, possibly described by some Feynman amplitude. And you take the classical limit, and you remove the discreteness, you remove the fuzziness. So the fuzziness is in particular given by the fact that in the quantum theory you have operators that do not commute, and in the classical theory you recover commutativity. And then you have a definition of a classical field in which from a probabilistic descriptions you obtain some equation of motion that are instead continuous equations, for instance in the formula of a differential equation. So in the case of quantum gravity, we have the same thing. So we have what I have presented to you in these hours was a bottom-up approach in which we look directly at the fundamental level, in which we have this quanta of space or quanta of space-time. And everything is discrete and careful. Here I am really talking about the quantum discreteness, and a different concept is the truncation. So we have discreteness, fuzziness, we have transition amplitudes, and then in the limit for h that goes to 0, in this, the classical limit is more complicated than h bar that goes to 0, but let me call it let me just consider this in a naive way. H bar that goes to 0, so is when you disregard the presence of this minimal length, the Planck length, you disregard the fuzziness, and you recover the classical field that is our beloved gravitational field given by general relativity. So here, something that has been emerging from our discussion is that we have this graph with which we work, and this graph is a truncation of the theory. And this is similar. So the graph that we have seen in the spin form, the one given by edges and faces and so on, provides the amplitude, and these amplitudes are a function of the boundary states. So the core of the story here is the fact that we have this kind of Feynman graphs that represents the evolution, where you have nodes that are like particles, and you have the edges in your evolution that are representing the evolution of these particles of this quantum time. And you have this graph that is making up your four-dimensional Lorentz spacetime. And we said at the beginning that this graph is a process, is representing a process, but at the same time, so a process like in quantum mechanics, but at the same time, it also represents space-time itself, or better, it represents some discretization of space-time. So you have then vertices that are like four-dimensional polyhedra, and you have nodes that are dual to three-dimensional polyhedra. So let's try to understand better the fact that we do computations in a truncation. And we were mentioning before the fact that one needs to show that the higher terms are just correction to the leading order in this truncation. But as we were saying before, it's always the case that we take truncations. For instance, also when we do standard quantum field theory, we always do computations in some truncations. And for instance, this is also what happened in, so the closest example to what we are doing here is lattice QCD, in which you wanted to describe, for instance, protons, and you don't need to take a truncation that is finer then you don't want to take a lattice such that this somehow go beyond just capturing the characteristic sides of your proton. So you adapt your truncation to be fine enough for the problem that you are addressing. But there is a fundamental difference with respect to what you do in lattice gauge theory or in lattice QCD. That is the fact that in lattice QCD, you have your fields that are living on this lattice, and when you perform the computations, you want to refine the graph, but you also want, in the end, to take the lattice space to 0. And this is something that is not available to you here. So it doesn't make any sense in this theory to take the lattice space to 0. So this is because the lattice itself that we are using, the graph that we are using, we said at the beginning, it's a diff invariant object. So imagine you stretch, you change your graph, but squeezing the links to 0 doesn't make any sense. So, so here, what you are left with is just a process in which a computational procedure in which you want to refine the graph without taking the lattice space to 0, okay? So this refinement of the graph is important for defining the classical limit. So the theory that I have presented, it's, if you want, oops, sorry. Yep. Here. The theory that I have presented to you is this one, okay? In which we have defined a transition amplitude for my two complex. So the question is, how do we go from here to general relativity? And I said, yes, okay, you can do this and go to Regge, and this result is well established if you have a single, a very simple object, like you have a single tetrahedra and you have small deficit angles. But first of all, the full definition of the theory comes with a limit that is for a refinement of my complex. So this is similar to what happens in the case of the Fock space. When you define the Fock space, in which you create and annihilate particles, in principle, your Fock space is defined with a limit for an infinite number of particles. But
Francesca?
Yeah.
We have a question here.
Let me just finish so we have the same here in quantum gravity, in which we do computations for a finite number of quanta of space that corresponds to do computation with a finite number of particles. Yes, question?
Yes, can you go to the previous slides?
Yeah, just.
Okay. Can you give me a little detailed description of what you mean by the excitations of the gravitational field?
So, can you repeat again? So you want me to comment on
the excitations of the gravitational field?
Yeah, okay. Yeah, so this is something I was saying even before. Yeah, you have a formulation of the theory in which describing excitations, like creation of quanta, comes more natural. So this is something I have not been talking about even though I keep on referring to it, that is the spinorial formulation of this theory. So if you know something about spinors that have to do again with SU2 and Pauli matrices and so on, I haven't discussed this, but I hope at this point you will find quite natural that you can introduce spinors in this theory. So when you have the theory formulated with the spinors, you can construct something that looks very much like creation and annihilations of quanta of space. And the reason why I was mentioning this before is because when you compute the graviton propagator, then what you're doing there is really like taking a given state, a given fixed space-time, in particular a flat space-time, a Minkowski space, and then you just look at excitations of your field, localized excitations of your field, and you look for correlations. Yeah, but I was just mentioning this in a very general way. I don't know, were you thinking about something else?
But my point is, LQG is the so-called background independent study or non-perturbative study. So I wonder how to construct the correlating operators.
Yeah. Oh, yeah, okay. So, very good. So, as I was saying before, so the computations that are done for perturbative quantum gravity are very reliable computations. Of course, they are not the full quantum gravity. They are an approximation of this theory that has been described in these lectures. So the point is that between telling that you have a quantum theory of gravity and you want and you recover general relativity, there is something in the between. So you also want to recover perturbative quantum gravity. So and it was a great success of the theory, the fact that in the belly of this formulation of quantum gravity, you also have the results that you obtain with perturbative quantum gravity. So it's like a low energy limit of this theory.
Okay, thank you.
Okay, good. Thank you for your question. Okay, more questions? Or maybe I can go back to the point here. That was, so I go back to this question of having a single quanta, the description of a single quanta, again, that you can think either as a fundamental quanta small, or it could be also just the quantization of a large region. And the relations between this and taking a refinement of your truncation of your graph. So of course, going back also to the previous question, indeed, you can think about each of these lattice sites as representing excitations of the gravitational field and therefore quanta of space, so the quanta of the field. And the point I was making is the fact that I have a formal definition of my theory that comes with the limit for an infinite refinement of my graph. But we should not confuse mathematical formal definitions with what we do in practice in the theory, because this is the same thing that we do all the time, as I said, for instance, with the Fock space. We define mathematically the Fock space with a limit for an infinite number of particles, but then concretely we do computations with a finite number of particles. So the formal definition of the theory sits here, and if you wanted to do things in a rigorous manner, to really get to GR, you should do this kind of process. You should take this limit, and then the limit that takes h to 0. Except that this is not a viable thing, because you never compute things in this limit, okay? So, and on the other hand, you cannot just do this limit because it works well in simple situations, but when you start to have a very complicated interior, very, very complicated to complex inside in the bulk of your system, then you don't get this limit in such a naive way. So what you have to do in more complicated situation, and again, this result was developed mostly by Mushin, is that you need to be careful and take these two limits together. So you take a high j or a small h bar together with the refinement. And of course, this makes things more complicated, but this is how things work. And in a peculiarity in this is the fact that this is different than what happens in standard field theory, and in particular, a peculiarity is the fact that there are no critical points in the sense that quantum gravity itself is a non-critical phenomenon. And to answer also the question from before, there is no infinity renormalization, and there is a physical scale of the theory. This is the Planck length. So this is what I was saying before. The theory that we have is a theory in which space-time emerges, but emerges in the sense that I can go from quantum to classical, and I have to be careful in the way in which I do this passage, and the theory that I obtain is a theory in which I go from a description term of quantum spacetime to the equations of general relativity, and careful, bringing with me all the peculiarity of general relativity, including the absence of a preferred time. So this is, in the classical theory, is not a peculiarity of the quantum theory. Questions at this point? Comments and curiosities and discussions?
On the previous slide, you mentioned that when you're sometimes the h bar to 0 limit to go from the LQG transition amplitudes to the Reggie Hamiltonian function is too hard. So you have to do the h bar to 0 and the refinement limit at the same time.
Yeah.
And like my, I guess this is a naive question, but in what universe is that easier than the simpler?
Well, it's easier. It's not that it's easier. It's correct. It's the correct thing to do. But Mushin, you are the expert, so I would like you to answer to that.
Oh, it's the intuition is because the approximation works for small deficit angle. And we know that the smooth geometry also has zero deficit angle. So there's no conical singularity. So which means these two limits has to be combined to get smooth geometry. So that's a very simple intuition.
Thank you.
There's a question there.
Yeah, my question is related to the continuous limit of the theory. I specifically want to ask, how can we even begin to imagine an answer to that question in the 4D theory in particular? I mean, so for instance, in the 3D theory, for instance, we know it's a topological theory. And we know, for instance, that the spin-form amplitudes, they are triangulation independent. In the 4D theory, with general relativity, that's out of the question. So how do we think about this question? How do we think about taking the continuous limit? I mean, is it related to the fact that we are sort of, taking the number of lattice points to sort of infinity? But then if we are doing that, then aren't we sort of removing that lower bound on the areas, on the volumes that we have, like we're removing the lattice altogether? So it's like, how do we think about this?
But that's exactly the point, that you take a refinement, but it's never a refinement. First of all, you have to remember, there is some confusion that people have regarding the graph, is that they think it in a very rigid manner. So it's like, I remember very bright people, a Nobel Prize, was making this argument that like you take a boost in your lattice, and so you are changing the dimensions of your lattice. So nothing is Lorentz invariant anymore. And the point is that this is not how the quantum theory works, because in this theory, what counts are the eigenvalues that you measure. So even if you have your system and you boost it, you keep on having your discrete spectrum for area, volume, and so on, and you keep on seeing the same minimal area, except that you will see the different eigenvalues with the different probabilities. So basically, when you do one of these transformations, you are projecting on you are putting yourself in a different basis. But so this changes the probability, but doesn't change the eigenvalues. So in this sense, in the theory, you never have really the disappearance of the minimal area and so on. But what is happening is the fact that you reach descriptions that is closer and closer to the continuous one. And as I said, I don't think the world is not discrete. Sorry, the world is not continuous. So, I mean, this table is made by atoms, but then I wanted to recover a description in which this surface is smooth and is described by some smooth equations. I saw a hand rising there. You wanted to add something, Carlo?
Maybe you're asking, how do I think about the continuous limit? That was your question, right? I think one can interpret this question in two ways. Let's go back to QED for a moment. QED a la Feynman with Feynman vertex expansion, okay? That's an expansion. So everything you compute it's up to some order in the number of vertices, whatever. Now you can ask, how do I think about the full limits of the exact amplitudes? And that can mean two things. On the one hand, abstractly, well, it's very easy. You just sum over all Feynman diagrams. That's how you think about it, okay? Concretely, that's the abstract answer. The concrete question is you don't. You don't, and that's okay, because you're not interested in the exact result. You're interested in a result good enough to compare your data within some error. So you hope that you could do that calculation. You don't. You hope it would converge. In QED, we don't even know if the series converges. The machine was reminding us. And concretely, you're perfectly happy with not going to the limit, just thinking that. Now, take this here, and it's the same thing. So the abstract answer is just that what Francesca is giving that. So compute this amplitude, the limit, take the two complex formed by maximum number of vertices up to n, take n to infinity, and you get the real continuous limit, okay? But of course you don't do that. You don't even know if it converged, like in QED. So you always describe the theory at some truncation. That's it. A different question, separate question, as Francesca was saying, it's how do I connect to the classical theory which is continuous? Well, in the same manner, you don't. I mean, the quantum theory gives some amplitudes, and you compare it with the classical theory amplitudes. Is this an answer to your question, or you were asking something more specific?
Yeah, no. This does answer it. So, like building onto this, say I take S4, for example, and I triangulate it by just a 1-4 simplex.
Okay, perfect.
And I do a calculation with the spin-form amplitude. Now,
Good.
suppose I triangulate it by 2-4 simplex.
Yes.
And do another calculation. I'll
Yes.
get different answers, right?
Yes.
So how do I make sense of this? I mean, which answer to trust, or
The second.
the second one?
Yes, you say yes, and then you compute with 4 vertices. So then two things can happen. Either you find, or you have hints, or you have argument to believe that the numbers stay the same, or your theory is bad. Okay?
Right, so
So concretely, some calculation which already have been done, for instance, Francesca was saying cosmology, show that by refining the two complex, you get numbers that look as converging. You get small corrections to what. So again, one question is what has been proved, and what question is what has not been proved, but one expects or one hopes, and seems to be the numerical results seem to indicate. A number of calculations, both in the way Mushin and the group here are doing numerically, and the way Bianca is doing, with not exactly with this amplitude, but similar amplitudes are doing, seems to indicate very clearly that if you keep refining, just the things converge. And sort of intuitively, once you start working with it, it's pretty obvious why, because it's really like truncating for the reason Feynman, not the Feynman diamond expansion, the Feynman path integral. You have a path integral, you discretize, and then you see that if you discretize more finely, it converges. For the same region, it seems obvious that this has to converge. But there's no theorem, no proof of that. There are indications. That's where the theory is.
thank you.
So I could say like a follow-up question. As far as I understand, like, yeah, taking C to infinity, it could be like the projective limit.
Correct.
But then, and I also understand what you're pointing out, and also like what the other comment that I did about the stopping on your series expansion. I do understand that, yeah, in quantum field theory it works out very well, even if you are like in the first loops. And that's a good approximation, or is good enough. But then this could mean that there is not like a proper way to go from the spin foam, from the covariant formalism to the canonical one, because the projective limit is like, we don't know the projective limit.
I would say that we don't know how to connect the canonical calculation and the covariant calculation. The Hilbert space is the same, the dynamics is different. But the reason we don't know how to do the connection in the four-dimensional Lorentzian theory, we sort of know it in the three-dimensional Euclidean theory in simpler cases, but much simpler. The reason is that because both sides are not clear enough and we can't do calculation, not a priori because of the projection, the projector thing. So much so that in three-dimensional Euclidean, where there is the same overall structure, there are papers that connect the canonical and the covariant. So it's just the complexity of the theory. It's not obvious because the sort of the evolution in the covariant is discrete, while the Hamiltonian constraint is sort of the infinitesimal. So concrete is, you know, intuitively in the best of possible world, there's a definition of functional integral. The functional integral gives a solution of the Will-DeWitt equation. So we should expect that the amplitudes satisfy the Hamiltonian constraint. But once you go concretely with these things, comparing one with the other, the languages are too different. Yep. Would you agree, Mushin, that this is the state of the connection between the, you've worked on both, so yeah.
The microphone, Mushin.
There is evidence when we study cosmology and black hole that we can extract some kind of Hamiltonian constraint semi-classically. Because both theory has very good semi-classical limit. Canonical theory and covariant theory, they both have good canonical, both have good semi-classical limit. So we can extract some connection at the semi-classical level and then go from that.
Yeah. So to connect the two things, what Carlo was saying is that this, you can think of the Hamiltonian evolution like being a infinitesimal version of the evolution. So the idea would be that if you take these amplitudes and then you look for states that are closer and closer, at a certain point you should see the connection. And on the other hand, as Mushin was saying, yeah, we have a number of works in which you can see possible ways to understand the connection. For instance, in cosmology, one of the first results we had was to try to extract what would be the operator that annihilates the amplitudes. So the amplitudes are projecting, the amplitudes are projecting on the physical states of the theory, and this is exactly the same that the Hamiltonian is doing. So the Hamiltonian operator acts on the Hamiltonian constraint operator acts on the states and gives you zero. So they do the same job, and in this sense, so what we were showing back then was that yes, you can extract an operator in this way using this kind of logic. Also, what Mushin was referring to was that starting from the canonical theory in cosmology, one can try to write down, basically you exponentiate the action, and you try to write something that looks like not a path integral, but a sum, a spin-form sum. And what was shown there was that you can rearrange your expansion so that it looks exactly like the spin-form one with all the different terms that mimic the one that we have seen here. It's like an expansion in vertices in a certain sense. But again, these are all indications that the convergence should be there, but it's not a final theory. Yeah, thanks. If there are no questions, how much time do I have, Mushin? 5? fantastic. So I want to show you that you don't have to go through all the complications of this calculation to extract meaningful physics from this, okay? So I believe that this theory is bringing us a lot of novel informations about the world. And if you are smart enough, we can focus on the content on these informations and do some interesting physics already with these elements. And I wanted to talk about something that is very dear to me because I've been working in cosmology. In particular, one of the great achievements of loop quantum cosmology is the singularity resolution. And the meaning that you don't have a Big Bang, but also you don't have other kinds of singularity that appears in the theory. And careful, this comes from the fact that the theory has a fundamental discreteness that is a space-time discreteness, and something that I hope we have seen at this point. So the question is, people in loop quantum cosmology has been proving over and over that you have singularity resolutions, and you can prove it for different choices of space-times that are more and more complicated. But can we have a sense in which the full theory, without taking any symmetry reductions or any complications, without considering any specific space-time, do we have a way in which we can read the singularity resolution in the theory? And in my opinion, yes, we can. And I ask you to think about the following situation. You are an observer and you are accelerating, okay? So the picture that I have here represents my Minkowski space in which you are an observer that is following this path, meaning you are accelerating. So notice that the acceleration here is inversely proportional to the distance from this origin here. And there were already ideas, heuristic ideas, that if you had a minimal length in your theory, you should have a maximal acceleration. But let's do this thing properly with all the informations, all the technology that we have built up in the previous hours. So in this picture, we can describe this what happened to this accelerated observer as being described by boosts, and in particular by a boost Hamiltonian. And so K, we saw in our theory, is the generator of the boost, and then AK is the generator of proper time evolution. So in this sense, we have an Hamiltonian associated with this. Now, we have learned that the theory, the dynamics of GR is described, is given by this relation between booster rotations. So proportionality between boost and between the K and the L through gamma. So the L, remember, are associated with areas. So I'm missing here. So my L are associated with something that is like E, G. And my boost operators are instead associated with something that is also an area, but it's like so with a time component. So I call a Lorentzian area, area here, an area that has this component that is defined in this way with a direction, a component in the time direction and another component in the space direction. So this object, so because we know that this object has a discrete spectrum, so we expect also this object to have a discrete spectrum. And in turn, this immediately produce a bound on the acceleration. So this is telling us that any observer that is accelerating in this space-time can keep on accelerating, but the acceleration has a maximum, has a bound. Now, there are theorems from the 80s and the 90s in which, motivated by heuristic arguments, people were studying a classical space-time with the imposition of a maximal acceleration. So all these works were indicating that unless you take a super funny, exotic space-time that you obtained by patching different space-time together and you do something very, very, very crazy, but for all the regular space-time we are interested in, cosmology, black holes, blah, 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 and so on, in all these cases, the assumption of a maximal acceleration implies automatically the absence of curvature singularities. So we have something in the theory that is telling us from scratch that such a maximal acceleration is a prediction of the spin form of the covariant dynamics. And in turn, we can use this information plugged in the classical theory, and we can say, because loop quantum gravity predicts a maximal acceleration, it also predicts that singularities in the form of curvature singularities cannot produce in the theory. And this doesn't matter whether you are doing a space-time that is homogeneous or inhomogeneous, or whether your space-time is isotropic or anisotropic. This is something that you expect to happen always. So this is kind of a heuristic argument, but to me it's very important that you can pick up informations from these transition amplitudes, from what we have learned with these transition amplitudes, and you can plug it directly in the situations that are relevant for the physics and are relevant also for the phenomenology. Do you have questions at this point? Also about singularities in general, or about this? All good? Oh, thank you, John. So it's gonna be a hard question. Oh my God.
I was just, I didn't quite follow you. So yes, from the simplicity constraint, you would have that these time-like areas, you call them, that would have discrete spectrum, but I didn't understand the connection between that and the maximal acceleration.
Oh yeah, I was pretty fast on that. So what the Lorentzian area does for you is that, so it means that when, so suppose, so you are an observer, for instance, moving here, that's very bad. and you consider the area that is spanned by this observer. So you will have a minimal acceleration that corresponds also, maximal acceleration that corresponds to the fact that you have this minimal Lorentzian area. Well, I don't know if, yeah, John, are you happy with that or? Okay. Yeah. Okay, and I want just to, so this is an example, in case you were frightened by all these spin-foam stories, a lot of representations and complications and calculations and so on. My message here is that there are things you can do even just taking a few informations from the theory and plug it into the physics you're interested in. And just to mention one last example that I cannot discuss in full detail, but a similar thing happens also for black hole entropy. So in the case of black hole entropy, what you can do is again to define a boost Hamiltonian. And from this boost Hamiltonian and the fact that you can have, let me see, sorry. A boost Hamiltonian and the fact that you can define a Uru temperature for an accelerated observer, basically you get directly a notion of entropy for the gravitational fields. So in this case, instead of dealing with a black hole horizon, you can do this construction even for a Rindler horizon that is just 1 point. But what these calculations were showing us were a number of interesting things. First of all, the fact that you didn't have to fix the value of the Barberi-Mirzi parameter to define a black hole entropy, because you could work simply in this way, using these relations here. And a beautiful calculation that was done in particular by Eugenio Bianchi was showing the equivalence between the black hole entropy with the entanglement entropy. Again, using this boost Hamiltonian and basically performing a computations that was a spin-foam computations, but bringing back my black hole, my entanglement entropy, and connecting it directly with the black hole entropy. So this is just a sketch of the many things you can do once you use this technology. So I think I want to, again, just to conclude here, I hope I have given you a bit of an idea of the variety of things you can do using this theory. You are going to hear more about this. You're going to hear about the numerics with Hong Wang. You're going to learn about the cosmological constant with Chao Ying. You're going to learn about how to use these computations in the case of black holes with Carlo. And you're going to learn this afternoon how to use these computations for cosmology. And I close here.